Hello students, so to discuss about ferroic crystals. Now these are the crystals which involve at least one phase which changes the directional symmetry of the crystals. At least one phase transition which changes the directional symmetry of the crystal, which changes the directional symmetry of the crystal. Now, the study of changes of symmetry as a function of temperature, pressure, etc. is a very developed subject. Now, when a crystal changes its symmetry, it is a process of going from one phase to another one, and it is called phase transition entailing a change of symmetry. Now, the term ferroic crystal or ferroics, in a general term, it covers ferromagnets. So let us talk about ferroic crystal or ferroics. It covers ferromagnets, ferrimagnets, antiferromagnets, ferroelectrics, ferrielectric, antiferroelectric, and similarly ferroelastic, ferrielastic, and anti-ferroelastic. All these things fall under ferroic. Now, all ferromaterial. So, a common thing about all these materials, they exhibit hysteresis. For example, considering a ferromagnetic material, a ferroelectric material will have polarization like this. This is a loop. We have polarization and electric field, P here and E here. This is a ferroelectric material. The same goes for a ferromagnetic material. You have magnetization with respect to the magnetic field, and we have a ferroelastic material. We have elasticity, tensor according to stress applied. apart from the domain structure, a second important feature of ferroic is the high value of certain response. So high response. First one, there is a domain feature. Second feature is it has got a high response. And there is a strong coupling. Strong coupling, and it is temperature sensitive. So these are the four important features of a ferroic material. Now in the ferroic materials, the important notion of prototype symmetry is in context of ferroic phase transition. So there is a prototype symmetry. It is in connection with ferroic phase transition. Now, the symmetry of any ferroic phase of a material can be regarded as derived by small distortions of prototype symmetry. So, this prototype symmetry, when it has small distortions, can be related to the symmetry of the ferroic phase. For example, let's take an example of BaTiO3. Barium titanate. It is called paraelectric material, like paramagnet. It is called paraelectric. Now, the symmetry of the cubic phase that means when T is greater than certain temperature, is a prototype for its tetragonal ferroelectric. Whereas, so we have a tetragonal ferroelectric material when T is greater than Tc, and when at room temperature there is a ferroelastic phase. So when room temperature is much less than T, ferroelastic phase. Of this material. So now this ferroelasticity must be a mechanical or elastic analog of ferromagnetism and ferroelectricity. So let's again. Ferroelasticity is the mechanical or elastic analog of ferromagnetism and ferroelectricity. Now, ferroelastic material, this has got a spontaneous strain addressed by spontaneous strain and concomitant domain structure. Domain structure. The word concomitant event which is naturally occurring. Now, due to this, the hysteresis is observed. When the bulk spontaneous strain is plotted as a function of applied directional stress. Ferroelastic crystal contains two or several stable states of orientation with no mechanical stress. So there is at least two or several stable states of orientation. With no mechanical stress. Now, it is possible to change reversibly one state to another by applying a stress indefined. Now, the existing stress strain elastic hysteresis with spontaneous strain and coercive stress. So, when we draw the hysteresis plot of a ferroelastic material, it is basically between sigma s, which stands for spontaneous strain, and sigma c, which stands for coercive stress. So coercivity is basically this region, and this is the spontaneous strain. Transition from ferroelastic phase to higher temperature phase termed paraelastic. So if we increase the temperature, so from ferroelastic phase there will be a transition to paraelastic. And it occurs by an increase in symmetry and change in the crystalline system. So it is basically an increase in symmetry and change in the crystalline system. Now these ferroics are of great importance in the family of smart materials. So these are basically ferroics are basically smart materials. And among them the most smart are the multiferroics and biferroics. Multiferroics and biferroics. Now, multiferroics has been coined to describe materials in which two or all of three of the ferromagnetism, ferroelectricity and ferrocrystal occur in the same phase. So here, all ferromagnetism, ferroelectricity and ferroelasticity, they occur in the same phase. It is called multiferroic materials. This means that they have spontaneous magnetization which can be reoriented by an applied magnetic field, a spontaneous polarization. So there is a spontaneous magnetization MS, there is a spontaneous polarization, and there is a spontaneous deformation or elasticity, sigma S, due to magnetic field, electric field and stress. Whereas these biferroics, these are materials in which two ferroic states occur in the same phase. The two ferroic states, it can be either an FM phi, ferromagnetism, ferroelectricity, or ferroelasticity, FEL, or any of two of the three, they occur in the same phase. Now, the materials with simultaneous ferroelectric and ferromagnetic are called, so we have a ferroelectric phase plus a ferromagnetic phase, then we will call it a ferroelectromagnetics. Secondly, the simultaneous ferroelectric and ferroelastic, it can be called ferroelectroelastics. Ferroelectroelastics. And lastly, with ferromagnetic and ferroelastic phase, they are called ferromagnetoelastics. So, ferromagnetoelastics. So any two of the three will occur simultaneously. It can be either a ferroelectric ferromagnetic phase, it can be a ferroelectric ferroelastic phase, or ferromagnetic elastic phase.